Okay, in this episode we're going to be looking at inclined planes and how to deal with those using our concepts of vectors. If you need help again, if you're looking for other sources of information, you can go to this URL in thephysicsclassroom.com and they'll talk about inclined planes. Okay, so a quick review of a couple of the key items. The normal force, again, normal does not mean regular, or average, anything like that. Geometrically, it means perpendicular to the surface. So if you're looking to figure out the normal force, just take your index finger of your hand, point it in the direction of the surface, and then your thumb should point naturally perpendicular in the direction of the normal force. An object upon a surface, the normal force is equal to the force of gravity. Now, it's not true it'll be equal in all situations. It's not true about rest or acceleration necessarily. But two things have to happen. There has to be no vertical acceleration. That way we have a balanced forces in the vertical direction. Summation of forces in the y direction would add up to 0. And the normal and the gravitational force have to be the only vertical forces. So as we've recently seen, if we pull with a rope at an angle, that's going to throw off the normal force. It will not be equal to the weight of the object. If the surface itself is angled, then there's no way that those two can be equal because gravity is going to point straight down. The normal force is going to point at some kind of angle. Okay, we're trying to get the forces right. There are three key forces to an object on an inclined plane. Key force number one is the same as all objects, the force of gravity, pointing straight down toward the center of the Earth. Now notice that's not perpendicular to the inclined plane, it's straight down toward the surface of the Earth. Now the normal force is the force that acts perpendicular to the surface, not the ground. So if you place your fingers in the direction of the surface, your thumb will point naturally up in the direction of the normal force. Okay, those are not forces, those are just things you can do to figure out the normal force if you're having trouble. Now this is a tilted surface, and it says the object is sliding down. Now as it slides down, we would expect there to be some kind of resistive force. Unless it's sliding really fast, it won't, or the object is really light, air resistance won't be so important, but the force of sliding friction will be. So we'll have some FFK working against us. Those are the big three, the most common three forces. Now again, you should notice they're not all lined up. That's going to mean we're going to need to do something to kind of force them to be lined up and to simplify this for ourselves. Okay, well, here's the big tip. When you encounter this situation when you're on an incline, just like when we had objects being pulled by ropes at an angle or pushed and pulled at an angle, we end up with uncooperative forces. So we need to deal with those uncooperative forces. The thing we're going to do is to turn them into two perpendicular components. Now, in this case, with the incline, this is a great situation, a great opportunity to adjust our XY axis. Instead of having our XY axis be to the right and up, we can rotate it, and we'll make our XY axis down the incline for the X and perpendicular to the incline for the Y. By doing that, we can already get any normal force lined up, and then we can bring the rest of them into cooperation with that normal force. Okay, so the gravitational force in that case then becomes the uncooperative force, because if we move our axis this way, then friction is lined up in the X and normal is lined up in the Y. We want to get that uncooperative gravitational force turned into a component that's perpendicular to the plane and parallel to the plane, and that's exactly what we call them. We call them the parallel force and the perpendicular force. Now, the thing that makes this really easy is the basic geometry of the situation. This triangle is similar to the triangle that the inclined plane makes. Therefore, this angle and this angle will always be exactly the same. So if we know the angle of the inclined plane, we can use that to determine the perpendicular force and the parallel force. Now the parallel force is on the opposite side of our triangle from the angle. So to find the parallel force, we will use the sine of the inclined angle, and we'll multiply that by the force of gravity. The perpendicular force is adjacent to the angle, so we will use the cosine of theta, and we'll multiply that by the force of gravity. Now once we've done that, keep in mind we're going to get rid of the force of gravity. We're going to remove the uncooperative force and replace it with these two components that make it up. So by doing that, we'll be able to get everything lined up in the x and y directions. Then we'll be able to go right on back and do everything the way we've done it in the past. This is just that intermediate step that's required to get everything to cooperate and line up. Okay, so we'll look at that quickly in this situation. We're going to look at whether the parallel force is greater than friction or less than friction, and so forth. Now, first one here, object is at rest. Therefore, all the forces have to add up to 0. That means the parallel force, which notice has been moved from down here to coming out from the center as in a free body diagram. Okay, again, vectors are mobile. You can move them anywhere you want as long as you keep them in the same direction and the same length. So the parallel force and the friction force actually have to be equal because we need a balance. This is going to be a situation of static equilibrium. The normal force and the perpendicular force are going to have to be equal. So again, this would be called static for stationary or at rest, and it's equilibrium because all of the forces add up to 0. The net force is 0. Now, if the object moves with constant speed, it's still going to be equilibrium, but instead of being at rest and static equilibrium, this will be a case of translational equilibrium. And in translational equilibrium, again, we still need all the forces to add up to 0. So the normal force and the perpendicular force are going to have to be equal to each other, and the parallel force and the friction force are going to have to be equal to each other. They still have to cancel each other out, but now that because we are in motion, we will stay in motion in a straight line at constant speed. Okay, now if we want the object to accelerate down the inclined plane, that indicates speeding up down the inclined plane. We don't want it to fall into the inclined plane, and we don't want to rise off of the inclined plane, so these two are still going to have to be equal. But to get the speeding up down the incline, then the parallel force is going to have to be greater than the frictional force. If we wanted to slow down as we move down the incline, then the acceleration would need to be opposite to the motion, and so then our frictional force would need to be greater than our parallel force. Okay, that's not called equilibrium, that's called acceleration. And again, the acceleration is going to be directly proportional to that net force. Same direction, and the larger the net force becomes, the larger the acceleration becomes. Okay, so that's the trick to working with an incline. We'll practice that a little bit in the next episode.